Good afternoon, everyone. Welcome to High Performance Computing, Advanced Scientific Computing course. We are here to continue on the lecture 13, Transformer Model and CFD Applications. In the second part of the course, we had a focus on the CFD application and how it's aligned to HPC and why HPC is important. We looked at the numerical approach of the CFD and why we need the HPC to run this simulation, and also we had example with some software like OpenFOAM, and we look at the deep learning model in this application. Today we will continue lecture 13 and we will present the recent and novel model of the deep learning, which is capable to be used in the fluid dynamic area with combination of the HPC resources. As usual in this course, we plan always to have a review on the previous lecture. Shortly, let's have a review and the recall of the lecture 12, which was lattice Boltzmann and CFD application. We point to some important feature of the lattice Boltzmann equation. First of all, it's working with a base of the mesoscopic scale, and we said this scale it's placed between the macroscopic and microscopic scale. We are not following the particle like the microscopic scale. However, it's based of the probability distribution, and based of this idea, we saw how we get to the equation of the lattice Boltzmann. There was a comparison between lattice Boltzmann equation and regular CFD, the traditional method. We saw some weakness of the CFD in contrast to the lattice Boltzmann equation. Additionally, regarding the high performance computing and parallel computing, because lattice Boltzmann equation working based off the two event, which is include streaming and collusion, it's great for parallel computing, and it's great part of it. And also for some limited application like post media, which regular CFD it's not work properly. It's working very well. However, still lattice Boltzmann in development, and many research going on this method to make it much more applicable. For example, in the turbulent flow application, one of the matter that need to be resolved in every lattice Boltzmann simulation is the viscosity, which is a complex term, especially when we are working with high values number. For the larger scale, the concept it's say the dominant feature based of the energy transfer between the large eddies, and the viscosity doesn't work too much, so it's required to specify the viscosity for the lattice Boltzmann model. However, for the small scale, the viscosity is the dominant player in the flow field. With this short review, let's go back to our lecture 13. In the lecture 13, we will have some introduction about the attention mechanism and what is it, and how it's led to the transformer model, and some part of the transformer model, like self-attention and positional encoding, how it's make it great to be used in the deep learning model, and it's a powerful model, which is basically we call it encoder decoder architecture, and we will discuss example from the fluid dynamic and how we can use the transfer model for it, and we will shortly look at the deep system to see how we can submit example of the transformer model training with data to make a prediction for turbulent flow. Then let's see the attention mechanism and its fundamental. Based on the literature, the idea of the attention and self-attention mechanism is relevant to the attention cues in the biology. In fact, based on the biology and uh, human study, the knowledge of the human when getting information from the environment doesn't possess all the information. In fact, there is a direct attention capability which only take fraction of the information of the interest to the brain and then focusing on that special part of that information. So this make the human uh, be capable with a lot of information, getting the point to focus on it, and without posting all the information with a long period of the time. When we mm, investigate these attention cues in the biology, so how the attention it's working with the visual world. Uh, this idea it came from William James in the 1890, and in fact, it's defined that framework the subject selectivity from the attention, both relevant to non-volitional cue and volitional cue. So this is the base idea. Therefore, we have two categories of cues. We can say two type of the cues and how they are working. That's making a human able or with a lot of information just taking fraction of the information and directly point to the part that is needed at the time when with the visualization gaining the information. Let's have an example to see how the non-evolutional cue and volitional cue are working. In the first example, in the right hand side, we have five objects, which are paper, notebook, and cup of coffee. Uh, when we are using the volitional cue, directly we are looking for a book to read a book. So without more posting among these five objects, we will look at the book between them. So this is the difference of the volitional cue, which directly find the object based of the aim. But in the non-volitional cue, which in the left-hand side, we have again these different objects. The idea is to look or find the thing which is uh, non-paper, and also we can say the red cup here. This is based on the comparison. So we will see what is between these objects. It's a non-paper. It doesn't made from the paper. So we are looking to the red cup. This is the criteria that how selection is working between these two different uh, selection, and this idea used to be modified and uh, in the attention mechanism, which is led to transform a model one of the powerful deep learning at this time. If we look on the simple uh, attention mechanism here in this figure, we can say the attention pooling is designed in this way that volitional cues, which is called query, can interact with the non-volitional cues, which here is called keys, and with values or sensory inputs, it can guide the bias of the selection. here in this figure, the keys, values, and the query, it's uh, displayed that how they are interconnected, and how the values make the weight for this data, and it's we can say it's making attention and self attention based off these model. So here we can see how when we have data input for the model, we two part of the attention, which is among all the data, and also self attention, which make the importance of each one and giving weight for them. This transformer working with data to give the output of the model. So if we want to have a look on its architecture, uh, in the beginning, the transformer used for language and the translation. So we can say the basic of the working with the input and output. Firstly, there is a general attention which work with going between the input and output element, and also there is a self attention which working with the input element. So let's see the example here that we have a sentence. How was your day? And which want to translate it to the French version. The attention mechanism, what is doing here? The word in the output sentence is map the important and relevant words from the input sentence, and these assign the higher weight for each of these words of the accuracy for the output of the prediction. This is what the self attention making, and which usually we say the encoder decoder capable to uh, make attention mechanism system between the input and output, and that is the power of the attention mechanism, which here we will look at the transformer model. When we look at the sequential model, like what we have in the recurrent neural network, and in the previous lecture we discussed it, and we said in the recurrent neural network, in the basic one, there was a vanishing gradient problem when we were working with long period of the data, and with some modification, like with long short term array, LSTM, and GRU, it's resolved. However, with the encoder decoder model, like attention mechanism, this working much better, because based of the uh, selectivity that is available in the uh, transformer model or attention mechanism, there is a mapping between the output and the input. So easily, the data from decoder, which is processing the output, have access to entire output sequence input, and so it's able to make a selectivity and pick out the specific elements from the sequence. Uh, Therefore, we can say in this mechanism, the focus and place more attention on the relevant part of the input sequence as needed, which makes it powerful, because mostly we're facing problem when we don't have history from the input, when we don't have enough information from the input, and we can't find a mapping between them, especially with long term of the data. So it seems the transformer with this idea, which mapping the output to all input in the queue, making this um, uh, challenge easier to work with long period of data, and we can use it for sequential model like time series. So we will look at the transformer architecture and how the different layer or step of in this architecture is working with data. Before that, let's point to the attention mechanism type, which basically there are two different major types, burden attention and long attention. The principle of attention of these two type is same, and the only difference is the architecture and the computation for these two different types. From bar down or attention, here you can see the step how the data is processed in these principles. However, the main change or aim of the improvement of this attention for the sequence to sequence model, it was for machine translation by aligning the decoder with the relevant input sentence and implementing attention. So this is the most change and important part of this model, which made to sequential model. But let's see how it's different with the long attention model. The long attention model, as we said, it has the same principle, but the main difference between these two, it's the way that the alignment score is calculated, and also the position at which the attention mechanism is being introduced in the decoder. For the long attention, there are three types of the alignment scoring function. Uh, However, in the Bahadano, there is only one type. Here we can see the difference between these two attention uh, mechanism, which is proposed, and we will continue to see how we use the transformer model based on this attention mechanism. In fact, this structure of the transformer include two level of the attention, we can say. When the input of the data came to the model, in fact we're feeding the model with sequence of the tokens into attention pooling, it will be uh, pairs of the key and values, which is also connected to query. Therefore, these generating one attention output, and also because these three terms, queries and key and values, came from the same place, this making the self attention level also uh, with the data. So with two level of this attention, we able to mapping the output to all input with this design, and making the model much more powerful than the regular sequential model like convolutional neural network or uh, recurrent neural network. The transformer architecture, this is the base diagram that presenting the transformer architecture. It came in the first paper of this work, which used for data processing. We can see it basically there is encoding and decoding part, and with the positional embedding is getting this power with the attention and processing the data and encoding them in the first part, and then going to the encoder. And again with the uh, multi-head attention in these two parts, as we said, it's make the great capability to make a connection and mapping between the output and whole input in the model. However, as we mentioned, we are interested to use this model for sequential application, which is in time series. Then we have a data with mm, correlation to the time. Then it would be great to input this data, which has a time correlation with the positional embedding. It's making uh, great training to the model to predict unseen data of these use case which has a sequential behavior. Here we have listed some feature of the transformer model, how it's working with the data which came in the original paper. In fact, the transformer model have encoder and decoder layers. The number of the encoder and decoder layers should be same as in the first original work. It had six decoder encoder layers. Of course, finding the number of the layer, there is no magic number, and it's required to examine and find the right number to have a optimum transformer model. Also, regarding the computing, which is the most important part in the deep learning, and we are talking about it in this lecture, about the computing power. In fact, when we comparing the transformer model with regular uh, sequential model like long short-term memory (STM) or gated recurrent unit (GRU), it's working with less layers. Less layers is mean less computing, so it's very important. Then it's mean with the same data, for example, if we are working with transformer, it's expected to get uh, speed up, and so we need less computing power. Furthermore, from the experience work also, when we work with high fluctuating data, it seems the transformer with same data has a much more power to get some extreme event or uh, fluctuation in the data. When we have a very noisy data, the transformer has a much better capability. With less training, it can able to get this fluctuation, which in our study or research we saw the LSTM need to work with more data training, more computing to be able to get this data. So these are some specific points related to the transformer, and it's making it, as you know, currently the encoder and decoder model a great option to work with sequential data. Here, I added this slide to see the statement from the main paper of the transformer, that how they explain the transformer publication and how it's they use significant improvement in the computational efficiency through factorization tweaks and conditional computations, while also improving model performance in case of the latter. So this is the main point that is uh, mentioned in the paper, which in the beginning uh, notified the capability of the publication of the transformer model. However, in the recent years, in this research, we had also in our research group and in the literature, it seems it's working very well, especially with large data. Uh, and in terms of the performance and accuracy, it's able to work much better than regular sequential models. Now let's see example of from the fluid dynamic CFD, and how we can use the transformer model to make a prediction for such data. This is of course a case study based off the data driven. The data from the experimental fluid dynamic, and in the previous lecture we discussed this, that there is a method that how we need valid data and reliable data to be used for training the model in the fluid dynamic community to be sure that this model result is reliable. Therefore, here in this study, we're using data from the experiment. The second point is finding the correlation between the input. In the first step, we designed to use time series of the velocity only as a function of the time. However, uh, to make the model much more general, we investigated this point that training each component of the velocity individually, which means one time we transform a model, we train the velocity component, for example, in the x direction, and in the other time we train on the y direction and make a prediction for them individually. The complexity of this model and how it's able to make a prediction, as we know, it's based off the uh, uh, PCA that it's working in the uh, deep learning model. But we try to understand what the correlation between different components. In fact, the velocity, a very important feature in the fluid field, which we are assuming it's carrying all the required information of the turbulent flow to be able to make a prediction. That's why when we are training a model with the velocity, it's gaining all the information, all hidden feature of the flow, then able to make a prediction. So let's point to this important matter that in the CFD, as we said, or in the fluid dynamic, we can say, we have experimental approach, which we said it's limited to some point. The analytical approach, it's not available only for few numbers of the turbulent flow uh, problems. The another approach, the numerical approach, and we said it's computational flight dynamics, CFD. In some terms, it's limited. First of all, if we want to have a very accurate solution and with high resolution, we need to use the direct numerical solution. And we said in the DNS, it's costly and required a large computation power to do that. These make it not interested option because of the limits of the power. In many terms, it's of course the HPC developing fast. However, we are still far to use the HPC for every size of the turbulent flow, especially with three dimension and with high Reynolds number. This is still the limit that we have on the meshing, on the memory of the computation and the processing of data, and also we have some terms that you specifying them in the CFD increase the computation requirement. For example, the gravity is a term when it's added to the numerical approach, it will add the other term for the computation and entering the computation power. So the computation power one limit, and also for some problem like Thomas media, the CFD doesn't work properly. And we mentioned for the CFD we need the boundary condition, initial condition to solve such problem. And in some use cases, this is also challenge to have all required information. To overcome on these limit and problem and going forward, always there is a step to find alternative or improve the method that's available. One other approach that we talked in the previous lecture was lattice Boltzmann, that resolving some matter that maybe are limited or difficult on the traditional CFD. And the other approach that in these days come, it's machine learning and deep learning, which is working with a data-driven approach. So it means we don't need to give a theory or analytical equation to the model, and it's working based on the data. However, the limit and the range of this model, where is it, is still unknown, and with every single use case getting much better the knowledge in this area. But it's good with the power of the HPC, working with large data from the fluid dynamics, from the turbulent flow, and study this phenomenon. In the lecture 11, we presented the sequential deep learning model. We used data from the turbulent flow with LSTM and Go, and we presented its capability. In this lecture, we will look on the transformer, which working based on the encoder decoder layers, and it seems it's working properly and it's able to capture much more detail from the training data to make a prediction. This is here a recall about the problem of the turbulent flow. As we know, it's unsolved problem in the classical physics. And here, the method we mentioned in the CFD could be used around LES and DNS. About the available hypotheses in the mm, term of the turbulent flow, there are two main assumptions on the basic hypothesis. Uh, One is homogeneous and isotropic, which uh, in the large eddies, they are completely not isotropic, and the small eddy mostly anisotropic. So this make this hypothesis working on the limit area. And also regarding the universal equilibrium theory, there are some challenge that Bachelor, for example, introduced the Kolmogorov hypothesis working on the universal equilibrium. So what when we have non-equilibrium system, what's happening? And also this figure presenting nice presentation of the energy cascade, how from the large scale, large size of the eddy, the energy transfer to the small one and split it to smaller size of the scale. So this is the base and the fundamental hypothesis that is available in the turbulent flow. However, because of this limit that we mentioned here, the Kolmogorov hypothesis has a limit range and also the universal equilibrium. The data-driven approach in the deep learning is great application because we don't need to feed the model or inform the model from the theory. Then it's working based off the data. Therefore, in our research, for example, in this area, we used a transformer model with four encoder and decoder layers. And you can see here the data. The blue color figure is presenting the velocity of the turbulence flow in the y direction, and the green one presenting the velocity component in the x direction. So we have two components that they are separated, and we can use these two components to train the model and make a prediction of them individually. These make the model benefit to be used, for example, when we have three components of the turbulent flow, can use them. I should mention here that these data use two components because the measurement taken with one high-speed camera in the uh, particle tracking velocity or Lagrangian particle tracking, and therefore we have only two components. To run the model and capture the information from the experiment with three components, it's required to have more than two camera to get the accurate data, and it's not actually subject of the research. The most important thing regarding the turbulent flow is a three-dimensional event. So it's required to simulate the turbulent flow in three dimensions to capture all the information. For example, in the CFD simulation. In the experiment, since we are working with real-world data, it means the data uh, carries all the information from the turbulent flow in three dimensions. But the only captured data during this measurement was in two dimensions. It doesn't meet this model, its lack of the information of the three dimension turbulent flow. Here you can see result of this model prediction for transformer. Here with 80% ratio of the data, that 80% training, we can see how much the prediction it's matched in the test part of this model, one for the x direction and one for the y direction of the velocity. Also, we reduce the training ratio to 60% to see how the model is working. Of course, the accuracy went down. However, still it's properly have a nice prediction, and it seems when we are going forward, it's losing its accuracy. So it seems, of course, the 80% training is working much better for this prediction. Now, shortly, let's go to the HPC system and present you how the running this work. You can use the deep system or area to run these transformer model training with the data and make a prediction for such application in the fluid dynamic, and you will see the environment of the uh, deep system. So let's have an example with the transformer and we see how we can submit a job. I'm using the deep system machine. Some of you have access to Elia and some of you deep. So I will run this example on the deep. Here, let's get access. If we want to have a look on the data that we have here, you can see the project if you have assigned before. Here we have the transformer. For this example, I want to run it. Let's look at the file that we have here. We have the batch script file here. We look at the setup on it. And this is the result from the previous one. Was this is the data which we use to train the model, and here the Python code for this model. So this is the requirement, and we will need to modify the batch file. Then we submit it. Now let's go to this directory. So let's go to the batch file. Here is the batch file. As you can see, we need to define the project that we are get access to it. Then we will specify the partition. You can see the partition that's available in your project. Here we are working with deep. We have different partition. This is a job name. You can specify number of the node and task per node and etc. And then here the module that is required for this setup, and here the command to run this work via the batch. So as you know, to submit the work, and the other file that it's required, as we said, we have the data and of course the code, the Python code, which is here. So we only need to submit the work and wait to see when it's getting the result. So this is the command. Then when we submit, we have the uh, job ID here. We can see what we have on the queue. Here is presenting us that the work is submitted and the job ID, and it's in the queue. And if we want to look on the detail of the work, of course, we can use the S-control show with the job ID. And here it's presenting us the work it's running. Then when it's done, you will see the result. And if you get some error, maybe you can look at the file of the error and the output and see how you can uh, do some modification on it. So this is the very short presentation of the example how you can submit a job on the deep system. And of course, in the similar way, you can use Elia. However, of course, the system information and the job script need to be modified based on that system. And you select the partition. So let's back. to the lecture and look at the result of this model. Here, I want to mention the hyperparameter optimization, how much is important. For example, in the studies that I presented here, we had the LSTM Go and the transformer. You can see in this table how the mean absolute error and R2 score and runtime for these different uh, model. In this table, you can see one of the column is Guru H, which is mean Guru hyperparameter optimization. This Guru model has a larger data than other three models that it's done before. But with hyperparameter tuning, it's get we can say higher accuracy and a shorter time. The data that used for this Go model, I can say it was double. However, the computation here is lower than two other models. So this is presenting the importance of the hyperparameter tuning for such model, and that's why it's very important to select the correct values for the hyperparameter in the deep learning model. Here also there are results from the speed up when increasing number of the GPU. As you can see in the table 2, there are same node number on the Joules booster system and also on the deep DAM module. Uh, with increasing the GPU on the Joules booster, the speed up getting reaching like more than 2.6 times than the first one GPU. And in the figure also we can see how it speed up the training of this model. And also in the table 1 is presenting the performance with these different models that we talk about them with similar data with 80% and 60% training. And also we talk the transformer is working faster with similar data set than Guru and LSTM. Uh, Regarding the hyperparameter optimization, here I'm presenting example. On the Joules booster, you can see with 4 GPUs. Here, the hyperparameter tuning works with the batch size per GPU, and you can see when the batch size increase, the mean absolute error it's uh, went down, and at the batch size of 512 is getting the minimum value, and again after that went up. So we found that this batch size per GPU is the optimum one. Therefore, the computing also time, you can see it's reduced to 255. When we had when we had 8 batch size, you can see how much difference between the computing sum. So the optimal optimization with the hyperparameter reduced the error and also increased the speed of this uh, model. To have a conclusion of from this application, we can say this model work with the data from the turbulence flow without any information from the hypothesis or analytical assumption. And it's worked properly. It's make a great prediction with 80% and 60% training with very high auto score. And this is based off the Lagrangian framework that we explain it on the lecture 11, that how we can find the correlation between the flow properties in the Lagrangian framework to the time as a time series and feed the sequential model like LSTM, GRU, and transformer, and also it's working with CNN based off this idea, then make a prediction for this data. This approach could help us to study the turbulence flow for longer period. For example, we can generate longer period of the data and study the turbulence flow, and also in some application, making prediction will help in some industry. So here we are ended with this lecture. Lecture 13, Transformer Model and CFD Application. There is a video here is presenting the self-attention deep learning on the transformers, and I suggest you to watch it. The link is available in the references, and feel free to contact me regarding the lecture or the data, and good luck in your final project.